So now in this section, 8.3, we want to look at the different mechanisms for elimination. We'll start off with just an overview, and then we'll go through each type of elimination. So it turns out that there are two mechanisms for elimination. There's the E2 mechanism, which is a bimolecular elimination. The 2 means that it is a second order elimination reaction. And E1 is a unimolecular, meaning it is a first order mechanism. Like the SN2, the E2 is a concerted mechanism, and like the SN1, the E1 is a stepwise mechanism. We'll find as we go further into the next couple of sections that there is a lot of similarities between SN2 and E2, and a lot of similarities between SN1 and E1. So let's start with the E2 mechanism and get to it in more detail. So in the E2 mechanism, it is the most common mechanism and the most useful for synthetic purposes. It is a concerted mechanism, as I mentioned. It has a second order rate law. So the rate is going to be dependent on both the concentration of the alkyl halide and on the concentration of the base. Here is an example of an E2 reaction. So here we've got tert-butyl bromide plus hydroxide ion as our base. You'll see we've highlighted one of the hydrogens that base is going to attack. And we're going to make a new bond between hydrogen and oxygen, break the bond between carbon and hydrogen, make a new bond between carbon and carbon, a new pi bond, and break the bond between carbon and bromine. That will leave us with the conjugate acid of whatever our base was. In this case, hydroxide has water as its conjugate acid. And then we'll also have bromide as our leaving group. So now on to a few details related to the E2 mechanism. All right, so here we've got the arrows drawn. Again, we're going to have 3 arrows. There will be 2 new bonds that are formed and 2 bonds that are broken. One of the new bonds that's going to be formed is the pi bond, and the bonds that are broken are, of course, between the carbon and the halogen, and the carbon and one of the beta hydrogens. So the base removes a proton or a hydrogen from a beta carbon, forming H2O, the conjugate acid of our base. The electron pair between the carbon and the hydrogen is going to move to make the new pi bond in the carbon-carbon double bond. And then the leaving group is going to leave with the pair of electrons that was between the carbon and the halogen. In this case, the bromine is going to take that pair of electrons and form bromide. Now, we'll find that there are quite a few close parallels between the E2 and the SN2 mechanisms. So we want to look at an energy diagram for the E2 reaction. Since, like the SN2, it is a concerted or one-step reaction, that means there's only going to be one transition state in our energy diagram. So that one transition state will look like this. Assuming that we're having an exothermic reaction, which is not always the case, but usually it's going to be either delta H close to 0 or a little bit exothermic, could be a little bit endothermic, but we're not going to have a huge endothermic reaction or a huge exothermic reaction. So there is our transition state species right here, and you'll see that that the difference between the reactant and the transition state, of course, that's our activation energy. The larger that activation energy, the slower the reaction, and then the smaller that activation energy, the higher the faster the reaction. Notice in the transition state that there is a partially formed double bond. It turns out that is important to the stability of the transition state, and we're going to discuss that here in just a bit. For E2 reactions, we need strong bases. If you recall, in the SN2 reactions, we needed strong nucleophiles. Well, in the E2 reaction, we need strong bases. So E2 reactions are generally run with strong negatively charged bases like hydroxide or alkoxides. And we saw some of those at the beginning of this chapter in the previous video. There are the two strong sterically hindered nitrogen bases that are sometimes used, DBN and DBU. We discussed those a little bit earlier in the previous video as well. It turns out these are, they're not as strong as hydroxide and alkoxide, but they're decently strong and they are non-nucleophilic. So they will deprotonate, but they will not act as a nucleophile. We also want to look here at solvent effects and leaving group effects. We'll find that as you increase the leaving group ability, the rate of an E2 reaction will also increase. So increasing leaving group ability increases the rate of E2. And here is a little spoiler. It also increases the rate of E1. And if you remember back to the previous chapter, it also increases the rate of SN1 and SN2. So in other words, leaving group ability, as you improve the leaving group ability, it will increase the rate of all of the reactions. And that's simply because the carbon-halogen bond is broken in the rate determining step for all of these reactions, regardless of whether it's first order, second order, regardless of whether it's elimination or substitution. That bond breaking is always going to occur in the rate determining step. Like with the SN2 reactions, we'll find that polar aprotic solvents will increase the rate of the E2 reactions. Polar protic solvents will more likely favor the E1 type mechanism. All right, so now we want to look at the effect of the alkyl halide structure on E2. This is where the similarities between SN2 and E2 start to part ways. So there are some differences here in the rate trends for the number of alkyl groups on the alkyl halide. So as the number of alkyl groups on the carbon with the leaving group increases, in other words, the more substituted the alkyl halide is, the faster the rate of the E2 reaction. And this is exactly the opposite for SN2. Remember, for SN2, what determined it was how much steric hindrance occurred at that carbon. But for E2, there is something different that's going on. And so we'll find that the more substituted the alkyl halide is, the faster the reaction will go. I'll show you why that is here in just a few minutes. Actually, we can look at this right now. So the transition state for an E2 mechanism, we are going to have a partially formed double bond. So because we have a partially formed double bond, that means that transition state has some double bond character. And to the extent that it has some double bond character, anything that stabilizes that double bond will also stabilize the transition state. Now, I will say that this effect is not as big as the effect that we saw with the SN1 reactions and carbocations. But it is a noticeable and measurable effect, and so it is something that we pay attention to. So as a consequence, a more substituted alkyl halide will give a somewhat more stable transition state. So more stable alkyl halides give more stable products. So here up on the top, we've got a primary alkyl halide. And when we eliminate that primary alkyl halide, we end up with a monosubstituted alkene. And that certainly is possible, but it's not going to be as fast as we would see with this reaction. And with this reaction, we've got a tertiary alkyl halide, which is tert-butyl bromide, or 2-bromo-2-methyl propane, if you want to look at it that way. And so here you'll notice we're eliminating this. And this would have quite a bit of stability from these alkyl groups to help stabilize the partial double bond character in the transition state. And you'll see here that we get a di-substituted alkene on this. So more stable products means more stable transition states and therefore a faster reaction. However, I will say it is possible for primary alkyl halides to undergo E2 reactions. They're just not quite as fast. And I mention this because in the SN2 mechanism, for when we do substitution, we can only do methyl primary and secondary. We can't do the tertiary. On this one, it's possible for primary, secondary, and tertiary alkyl halides to all undergo E2, but the tertiary alkyl halides go faster. All right, and here is a summary of the E2 mechanism, and then we will look at a problem number 12 here in just a second. So again, the kinetics is second order, and again, that's what the 2 means. It's second order, bimolecular. The step is a one-step or a concerted mechanism. Tertiary alkyl halides go faster than secondary, which go faster than primary. It is favored by strong bases. And like with all of our reactions, the better the leaving group, the faster the reaction. And for the solvent effects, we'll find that polar aprotic solvents will favor the E2, just like it favors the SN2. All right. So here we want to look at how does each of the following changes affect the rate of an E2 reaction. And just as a reminder, the rate is equal to K times the concentration of the alkyl halide times the concentration of our base. And we don't know what the base is. This is just a generic reaction. So how does the following affect it? If we triple the concentration of the alkyl halide, we'll see that there's a direct relationship, so that will also triple the rate of the reaction. All right. If we have the concentration of the base, well, having the concentration of the base will have the rate of reaction. All right, changing the solvent from methanol to DMSO. Well, DMSO is a polar aprotic solvent, whereas methanol is a polar protic solvent. We'll find that E2 reactions are favored by polar aprotic solvent, so this will increase the rate. Changing the leaving group from iodide to bromide. While bromide is a very good leaving group, it's not quite as good as the iodide, so this will decrease the rate of reaction. But just as a note, it will probably still be plenty fast. All right, changing the base from hydroxide to water. So hydroxide is a strong base, and we know that strong bases tend to favor the E2 mechanism. So changing it to water is probably going to decrease the rate. All right, and then changing the alkyl halide from CH3CH2Br to CH3-2CHBr. So here we're changing it from a primary to a secondary. We know that the more substituted the alkyl halide is, the faster the reaction. So this will increase the rate of reaction. All right. So make sure that you, when you're going through this again later, make sure that you understand why each of these is true. All right. We want to look at something that we refer to as Zaitsev's Rule. And Zaitsev was a chemist who came up with this rule. And what Zaitsev told us is when alkyl halides have two or more different beta carbons, we know that more than one alkene product can be formed. Well, the Zaitsev rule tells us that the product that we're more likely to form, that we're likely to get more of, is going to be the more substituted alkene. So Zaitsev's rule, the major product is the more substituted product, or the more stable product. All right, so that is what Zaitsev's rule tells us. On this one, just to point out what's going on, we've got two different types of beta hydrogens. We've got the beta hydrogens that are on the ring, and when we eliminate those, we're going to get product A. So if we eliminate across this carbon-carbon bond, we will get product A. You'll see that's tri-substituted. And if we eliminate the beta carbon that is the beta carbon that is the methyl, we eliminate across this bond, we will end up getting this exocyclic as a minor product. So we would definitely have a selectivity here where we got more of A than we did of B. We call this regioselectivity. So a reaction is regioselective when it predominantly gives us one constitutional isomer over another possible constitutional isomer. Here is another example. It's 2-bromo-2-methylbutane. So here's the 2-bromo-2-methylbutane. We have the possibility of eliminating across the carbon-1, carbon-2 bond. And when we do that, we'll get a carbon-carbon double bond there. And that will be a di-substituted alkene as our product. When we eliminate across the carbon-2, carbon-3 bond, so between our alpha carbon and beta-2 here, we will end up getting a tri-substituted alkene. Because there is some of the double bond character in the transition state, that means that this top one is a less stable transition state and therefore higher in energy, and it's going to have a higher activation energy. As a consequence, we will get less of this product. This one is a more substituted alkene, or has more substituted alkene double bond character in the transition state, and therefore it will be a little bit lower in energy, and we will get our major product, which is our tri-substituted alkene. So E2 reactions are regioselective. All right. We also have stereoselectivity, which we will get to in more detail a little bit later, but a reaction is considered stereoselective when it predominantly forms one stereoisomer over another. In the case of forming alkenes, this is going to be when we form a transalkene versus a cisalkene. So in this particular reaction, we know that it is possible. To eliminate across this carbon-carbon bond. And when we do that, there's two possible ways that we can form product. One, we could have the trans product, all right, and one, we could have the cis product. Well, we'll find that the trans product, it gives a more stable product, but it also has a more stable transition state, and therefore we get more of it. Now, we'll discuss stereoselectivity a little bit more, but I want to look at regioselectivity and talking about Zaitsev's rule in problem number 34. So let's switch over to our document camera here and look at our possibilities. All right, so here we've got our strong base. These are all going to be E2 reactions. We've got our strong base. Here's our alkyl halide. It's a secondary alkyl halide. And we want to look at the different possibilities. Well, there are two different types of beta hydrogens. Now, I'm going to label this. So 1, 2, 3, 4, 5, 6, 7. There's 7 carbons. And we have beta carbons with hydrogens on carbons 1 and 3. And so we can either eliminate across the carbon 2 bond, or across the carbon 2, carbon 3 bond. So let's draw both of those. 1, 2, 3. And so this would be eliminating across the carbon 1, carbon 2 bond. And this would be eliminating across the carbon 2, carbon 3 bond. All right, now which one would be the major product? Well, this one would be our major product. All right, I do want to point out that we would get a stereoisomer of this. We would get some of the cis isomer in addition to this trans isomer, but that is not part of this particular problem. We will deal with that at a later point in the chapter. All right, so now we want to look at this one. So we'll label the carbons on this. So 1, 2, 3, 4. And here we really only have one possibility. The only beta carbon with hydrogen is carbon number 2, because our alpha carbon is on the end. So we're going to have to eliminate across the carbon 1, carbon 2 bond. And so we will end up with only one constitutional isomer as a product. If you're wondering what this thing on the end is, it is a protecting group. And we will talk about protecting groups at a later point next semester. All right, so that would be our elimination product, and it would be the only product that we would form. All right, on this one, I'm going to label this one again with numbers. So 1, 2, 3, 4, 5, 6, 7. It turns out that there are three different, and I'm going to scoot in just a smidge here. All right, there are 3 different carbons, beta carbons, with hydrogens. Carbon 3 has 1 hydrogen on it. Carbon 5 has 2 hydrogens, and then this methyl is also a beta carbon with hydrogens, has 3 hydrogens on it. So we can get 3 products. Let's go through all of them. We'll start with 3. So 1, 2. All right, so if we eliminate across the carbon 3, carbon 4 bond, we will get this. All right, if we eliminate across the carbon 4, carbon 5 bond, we will get this. And if we eliminate across the carbon 4 methyl bond, we will get this. Now, not surprisingly, we'll get the least of this because that's di-substituted. This one's tri-substituted. But if we look at this one, that one is tetra-substituted, and that will be our major product. All right. Again, we are ignoring stereoisomer effects. It turns out that these two also have cis-trans isomers that we are ignoring at this point. All right, on this next one, 1, 2, 3, 4, 5. So you will see that we have 5 carbons, and we're going to eliminate across. We've got 5 carbons. The alpha carbon is carbon 1. That means our only beta carbon is carbon 2. So we have to eliminate across the carbon 1, carbon 2 bond. And so that will be our only product. That will be our only product. All right, on this one, let's go ahead and count these. So 1, 2, 3, 4, 5, 6, 7. So we've got seven carbons, and our alpha carbon is carbon number 1, and our beta carbons are going to be carbon 1 and 3, carbons 1 and 3. So that means we have 2 possible constitutional isomers. If we eliminate across the carbon 1, carbon 2, we'll end up with that. And if we eliminate across the carbon 2, carbon 3, we'll end up with that. So this one's mono-substituted, this one is di-substituted. So of course this is going to be our major product. All right. On this particular one, I'll go ahead and label this. So 1, 2, 3, 4, 5. And the labeling doesn't matter except for just communication purposes. We do have beta carbons with hydrogens at carbons 2 and 4. So if we eliminate across the carbon 2-3 bond, it'll be here, and the 3-4 bond, it will be there. So let's do that 3-4 bond first. So we get that. And then we'll do the 2-3 bond. Would be that. If we look, this one is a tri-substituted alkene, whereas this one is di-substituted. So since this one's tri, this one will be our major product. All right. So now we want to look at the E1 mechanism. And the E1 mechanism is different. It is first order, right? It has a lot in common with the SN1 mechanism. In fact, the first step is exactly the same. So it does consist of 2 steps. The first step is the rate determining step, and it's also unimolecular, and that is the breaking of the carbon-halogen bond to form a carbocation. And so that one is here, and like I said, that is the slow or rate determining step. That's an endothermic step, pretty significantly endothermic. All right, so we form that carbocation, and then the second step is when we deprotonate. So our base comes along, removes the hydrogen, and forms our alkene. This one is a relatively fast reaction. Since the first step is rate determining and the first step only has one component to it, that means that that will end up being the only thing in the rate law. So the rate will be equal to K times the concentration of our alkyl halide. And in this case, it's the tert-butyl iodide. All right. Like with the SN1 reactions, we will find that the E1 mechanism is favored by polar protic solvents. So it will be favored by polar protic solvents. So here is an energy diagram for an E1 reaction. So an energy diagram for our E1 reaction. Our first step is the rate determining step. All right, and that is has this large activation energy. We have a carbocation intermediate, and so that carbocation intermediate, will be formed. The second step is relatively fast. It has a much smaller activation energy, much lower transition state energy than our first transition state. And our product is down here. So the way this one is drawn, we have an overall slightly exothermic reaction. So we do want to be able to look at the transition states for both the first and the second step, but the first step is going to be the important one because it is the rate determining step. The rate trend for primary, secondary, and tertiary alkyl halides with respect to the E1 reaction is that we will find that the rate will increase as we increase the number of alkyl groups on the alkyl halide. So tertiary faster than secondary, faster than primary. The reason for this and the explanation for this is that the product of the first step, that intermediate, is a carbocation. And the more stable that carbocation is, the lower in energy our transition state will be. And the lower in energy the transition state is, the faster the reaction. So we'll find that the more substituted alkyl halides will give a tertiary carbocation, which lowers the energy of the transition state, which makes the reaction go faster. So again, since that is an endothermic step, our Hammond postulate says that anything that stabilizes this carbocation, in other words, more substituents, will also stabilize the transition state and speed up the reaction. All right, looking at the effect of base strength on E1 reactions, we'll find that the strength of the base usually doesn't cause it to do E1. What it does is it helps us to determine whether we're going to have an E1 or an E2 mechanism. Since both the E1 and the E2 reaction are favored with more substituted alkyl halides, then we need to look at how strong the base is, and the stronger the base, the more likely it is to favor an E2 mechanism. The weaker the base, the more likely it is to favor an E1 mechanism. So strong bases like hydroxide or alkoxide are going to favor E2 mechanisms, and weaker ones that are neutrally charged, have no charge, like water and alcohol, will favor the E1 mechanism. Regioselectivity, we'll find that Zaitsev's rule also applies to the E1 reaction. So more substituted alkyl halides will give us, the products will be more substituted alkenes. So here we've got two possibilities as far as the alkenes. Here, if we eliminate across the carbon and one of the carbons in the ring, then we will end up getting this tri-substituted alkene. Whereas if we eliminate between this alpha and beta carbon that is the methyl, then we will get this di-substituted alkene. So E1 reactions are regioselective like E2 reactions. All right, and then finally here, we want to look at our summary for the E1 mechanism. The reaction kinetics are first order. We'll find that the mechanism is going to be two steps. The first step is our rate determining step that forms the carbocation, and the second step is the deprotonation with our base to give us the alkene. We'll find that more substituted alkyl halides will go faster. They'll react faster than the less substituted alkyl halides. We'll find that the base is the reaction will be favored by weaker bases such as water and alcohol. So if you have a strong base, that's much more likely to favor an E2 mechanism. An improved leaving group will increase the rate of the reaction, but the increased leaving group ability will increase the rate of all of our reactions, E1, E2, SN1, and SN2. And then finally, the solvent is going to be favored by polar protic solvents rather than the polar aprotic solvents. So E1 reactions often will occur with competing SN1 reactions, and so the E1 reactions of alkyl halides are not quite as useful. We're going to discuss this in a couple of minutes when we look at the next page, but for now we are going to look at numbers 40 and 41. So we'll switch over to our document camera here. All right, what alkene is the major product formed when each alkyl halide in an E1 reaction? So we're just going to write down the major product, and our major product we should eliminate across this carbon-carbon bond, and so we should get a tetrasubstituted alkene. All right, and here we'll still write those CH3s on there. All right, so that would be our major product. That would be our major product. It's not asking us to write minor products, so I'm not going to write them, but that would be our major product. On this one, we've got a couple of different possibilities. We could eliminate here, or there. Turns out these two carbons are identical. If we count from this side, that's carbon 3. If we count from this side, that is carbon 3. So, so that would give us a tri-substituted, and if we eliminate it across here, that would give us a di-substituted. So our major product here is going to be 1, 2, is going to be that. All right, on this one, we've got 1, 2, 3, 4, 5, 6. And let's see, we've got, and so we would eliminate across these two to give us this alkene. Now the other possibility is if we eliminate over here, we would get the alkene on the end, but that one would be di-substituted. This one is tri-substituted. So that is the major product for each of those reactions. All right. So now on number 41, draw all the constitutional isomers formed for the elimination of each reaction. And then label the reaction as either E1 or E2. So here we're trying to determine, is it going to go by an E1 mechanism or is it going to go by an E2 mechanism? So we can look at, well, the alkyl halide will tell us something, right? Because E2 can happen for primary, secondary, or tertiary. E1 can only happen with secondary and tertiary. So if we have a primary, then our only possible pathway is going to be E2. Our biggest hint is going to be whether we have a strong base or a weak base. If we have a strong base, it's probably going to be E2, and if we have a weak base, it's probably going to be E1. In this case, on the first one, we've got a strong base, so this is definitely going to favor the E2 mechanism. And we have two possibilities. We can eliminate across carbon 1, carbon 2, or across carbon 2, carbon 3. So if we eliminate there, that would be carbon 1, carbon 2. And here, if we eliminate across carbon 2, carbon 3, we will get that. All right, and it doesn't tell us to say which one is going to be the product. However, I'm going to go which one will be the major product. However, we'll go ahead and do that. This will be our major product because of Zaitsev's rule. So it would give the more substituted alkene. Now on this one, we're going to get the same exact products. It's just that it's going to happen by a different mechanism. Because this is a weak base, this will prefer to go by an E1 mechanism where we have a carbocation intermediate. But as I mentioned, our products would be exactly the same. So that would be our major product. 1, 2, 3, 4, 5. On this one, we've got a primary alkyl halide. And with a primary alkyl halide, that eliminates the possibility for doing an E1 reaction. So that means that this one has to go by an E2 mechanism. And that's good because here we have a strong base, so the E2 mechanism is going to be favorable anyway. So since we only have one beta carbon with a hydrogen, which is the carbon number 2 here, that means that we only have one product. So 1, 2, 3, 4, 5. We will eliminate across the carbon 1, carbon 2 bonds. Okay, so on this one, and I'm going to go ahead and label this one because there's a lot going on here. We've got 1, 2, 3, 4, 5. All right, and so there's a couple of possibilities. We could eliminate across the carbon 1, carbon 2 bond. We could eliminate across the carbon 1, carbon 5 bond. Or we can eliminate across the carbon 1 CH2 bond that is on this propyl. All right. Now, as far as the mechanism goes, we've got a weak base, and so this is much more likely to follow an E1 mechanism. And you'll also see, since it's water, that is a polar protic solvent, which also favors an E1 mechanism. All right, so 1. Let's do carbon 1, carbon 5 first. All right, so there's a double bond there. And we'll do carbon 1, carbon 2. And then we'll also do the carbon 1 and the CH2. All right, and Jen, as far as what our major product would be, we would predict this would be our major product. It is the most substituted. All right, on this one, our 2 beta carbons are identical. So if we eliminate here or we eliminate there, we're going to get the same product. All right, so it doesn't matter. 1, 2, 3, 4, 5, 6. Carbon 2 and carbon 6 are identical. So like I said, it doesn't really matter. It doesn't really matter whether we do 1, 2 or 1, 6. So if we eliminate there, we'll end up getting that, and that will be our only product. And then finally here, 2, 3, 4, 5, 6. Carbon 1, carbon 2 versus carbon 1, carbon 6 are going to be different. So we'll get 2 different products. So if we eliminate across carbon 1, carbon 2, we'll get that. And if we eliminate across carbon 1, carbon 6, we will get that. As far as these go, we're probably not going to have one that is favored over the other because they are both di-substituted alkenes. So those should be approximately equal in likelihood. All right, well, that is a good place to end this video, and we will resume this by looking at section 8.7, and we will do that here in just a few minutes.